Everyone, this video is a tutorial about the usage of structures. In order to follow this video, please download the file structures_stud.ipynb. This one is in the folder 6 on OLAT. So once you open the file, you should see this. There are a couple of markdown comments and empty code cells, and we are going to fill these code cells. The aim of the tutorial is to show you how to construct some basic structures with Julia. And what we are going to do is to simply generate a structure that you could use to store and order samples you would have been acquiring during a field campaign. So we are going to generate a first structure now that will contain geographical coordinates. Let's call it position with longitude x, latitude y, and altitude h. So this would be the coordinates at which you have been sampling a piece of rock during a field campaign. So let's create this structure. You start with the word struct, and then it needs to be followed by the name of the structure, which is here position. A struct finishes with the statement end, and we want to have x, y, and h inside. X, y, and h. So that's our struct position. Now with Julia we can go a little bit further. We can also assign a type to each of these variables. X, y, and h are all going to be float 64. They are not integer numbers, they are not characters, they are not strings. Coordinates will be represented with a floating point number. And this is how to do it. You put twice the colon sign and then you type the type name. So twice semicolon and float. Now you press play. Of course we need to make sure that Julia is the active kernel. There we go. Get a green tick mark. The struct position has been created successfully. When you do a field campaign, you will obviously also make some measurements about layer azimuth and layer dips. In order to store the information of layer azimuth and dips, we will create an additional structure that we will call layer orientation. So let's go for this. We create a new struct which we call layer orientation. We finish with the word end, and again we will add the information. So AZ will be the azimuth angle and dip will be the dip angle. AZ is a float 64 and dip is also a float 64. Next, we're going to create a structure which will define the sample. And this structure, we will call it sample. It will contain 4 fields. The name of the sample of type string, the type of rock, another string, the position, which is of type position, what we just generated here, and the layer, which will be of type layer orientation. What we have, the type we have been created here. So let's start. We create the structure sample, finishes with end. We have name, which is a string. We have rock, which is also a string. We have position, which is of type position. So now you should understand that position will actually be a structure. So the structure will be nested. Inside sample there will be position, which is itself a structure. This is a nested structure. And then we have layer, which is of type layer orientation. It is again a nested structure. So layer will be layer orientation here. Let's press play, and we get a red cross. So what did I do? Yes, I forgot to press play on that one, so I have to activate this cell. Now I get a green tick mark such that layer orientation exists, and now I can press play here. Layer orientation exists and everything is fine. So now we can generate a first sample. So let's generate the first sample. So the first sample, we will call it S1. And to create an instance of the structure sample, we need to give the 4 arguments. The name of the sample, the name of the rock type, the position of the sample, and the layer orientation. So the first argument will be a name that you choose for your sample. I will call it S1. And then we define the rock type. So here it's going to be a gabbro. Now we need to set the position. So we create an instance of the structure position here. X coordinate 10. I'm deciding it now. Y coordinate 10 and altitude 1. And the last argument which is needed is the layer orientation, which is also an instance of structure layer orientation. Now let's give an azimuth at 15 degrees and a deep angle of 20 degrees. So if you press play, you will see the output here. Name S1, gabbro, position 10, 10, 1, layer orientation 15, 20. That's the first thing one can do. Now, how can we access the fields we have just entered in there? So to access the fields, you can simply do S1 type name, then it will extract the name. S1 dot rock, you will get the type of rock. And now, if we want to reach the position, we type position with the lowercase p, because it is one of the fields of the structure. And then inside position itself, we will reach the field, for example, X. So let's press play, and then it will give you 10. So this holds for all of the fields. So we can access H, for example, or you can access layer dip, and that's how to recover all this information. Now, we will consider several samples. All the samples will have the same type. They are all of type sample. So all of these samples are one instance of a structure sample. We can put all our samples in an array of samples. Remember, arrays, they can store quantities of same types. So here, it's one way to store different instances of the structure. So to generate an array, remember, we will use the square bracket. So let's give a name to our array. We will call it samples. We make it equal to open bracket, close bracket. In there, we will generate the samples. So let's generate the first sample. So the sample 1 will have a name S1. Again, it is a Gabro, and it was sampled at the position 10, 10, altitude 1, and the layer orientation was 15 for the azimuth and 20 for the deep angle. Now let's add some more samples, sample 2. So let's be lazy and apply copy paste. Sample 2 S2 is also a Gabro. It's taken as a position x20 and altitude is 2. The layer orientation is 22 and the angle is 25. And let's create the last sample, sample 3. This time it is a granite, x position 25, y 30, altitude 9, azimuth 124, and deep angle is 33. Let's press play. There we go. We have generated a vector of samples which contains 3 elements, 3 different samples. Next thing we can do here is to list all the elements of this vector. So as usual, when you want to access all elements, you can use the colon sign. If you want to access one element, you can do sample 1, sample 2, sample end will give you sample 3. So now let's extract the data we have stored in this structure, but let's extract the data as an array. So let's say I want to extract all the rock types of all the samples. So one way to do this is to use the function getField, which I mentioned during the lecture. The function getField is a direct way to do this. So getField receives 2 arguments. The first is the name of the array here, the array of structures, and then we should give the name of the field we're interested here. So once again, this is a function, this is a vector, and this is the name of the field. If we want this function to apply to the whole vector, we need to broadcast the function, and for this we need to put a dot here. So let's press play, and there you go. getField has extracted all the rock type names from the list of samples into a free element vector of strings. So now we have extracted this. Let's do one thing which is more complicated. You remember that we have nested structures. So we have put the structure position inside the structure sample. So let's try to generate a vector of all the coordinate x. So we use again getField. So we will do the getField. But instead of looking for rock, we look for x. But can we look for x directly into samples? No. We first need to look, we only can look for x directly inside position, which is inside samples. So the way to do this is to apply getField twice, basically. So first, we will extract position from samples. That's what we do here. We extract all the positions from sample, and then we extract all x coordinates from all positions of all samples. So let's play here. Green cross. Then it worked. 10, 20, and 15. These are the coordinates x of all the samples extracted within a free element vector of float 64. So let's do a last exercise. Let's loop over the array of structures and print out the information of each sample. So if we want to loop over an array, we'll use the statement for, and we will give an index name I, which will range in each index of samples. So basically it will go from 1 to 3 because there are 3 samples. And now let's print the information of each of the samples. So we'll use println. Let's create a shortcut here. So we create a local variable s, which will be sample of index I. So s will first be equal to sample 1 if I equal 1. When I equal to s will be the structure of sample 2. And when I is equal to 3, then s will be equal to sample 3. So we print a string sample next argument, let's put the name. S is our structure dot name. Let's try to see if this works. I missed an S here. The array is called samples. There we go. We have a loop running over all the samples, and we are printing the name of the sample. Sample S1, S2, and S3. And then we can add more information. So we can continue building a sentence. Sample S is A. And then we will put the rock type S rock. Sample S1 is a Gabbro, sample S2 is a gabbro, and sample S3 is a granite. And so on. So we could print the position X, Y, the altitude H, but also the layer coordinates. So I think that's enough for this example or tutorial on manipulation of structures. And I will thank you for your attention.